Hi, welcome back to my channel. My name is Gina. In this video, let's talk about the lines and planes in R3. A line in R3 is determined by a point and a direction. Here's an example. It's given a direction vector D, where the direction vector is non-zero, and it's given a point P0 that is on the line L. Then any point on this line can be characterized in this form. In vector form, we have P, which is any point on the line, equals one point on the line, P0, plus a free variable, T, times the direction vector, D. Or we can write out the x, y, and z component, and that gives us the parametric form of the line L. So for each component, there's a constant, which is the corresponding coordinate of P0, then plus the corresponding component of direction vector D times the free variable T. From the parametric form, since we are simply writing all the components from the vector form, so for a point on the line, the free variable T in the parametric form should be the same. So we can also solve for T and equate the three equations. Suppose from the x component, from the parametric form, we have x equals x0 plus a times t. If we solve for t, then we get x minus x0 divided by a. Similarly with the other two components. Then, if we equate all three equations, we get this equation, x minus x0 divided by a equals y minus y0 divided by b, and this equals to z minus z0 divided by c. And this also describes the same line, and we call this form the symmetric form. We can interchange the two notations. When a line is given in parametric form, we can rewrite that in symmetric form and vice versa. Let's look at this example. In the first example, the line is given in parametric form, and we want to rewrite the line in symmetric form. To write in symmetric form, we need to isolate for t. From the x component, if we isolate for t, we get x minus 1 divided by 1. If we isolate the t from y, we get y minus 2 divided by negative 3. And if we isolate for t from the z component, we get z plus 1 divided by 2. In the second example, the line is given in symmetric form. We want to rewrite that in parametric form. To do that, we are going to solve for x, y, and z. Then, for x, we get x equals 3 minus 2t, and y equals 5t, and z equals negative 1 plus t. How about the point P0 and the direction vector of these two lines? The first line, we have point P0 at 1, 2, and negative 1. And the direction vector is 1, negative 3, 2. In the second line, P0 is at 3, 0, and negative 1. And the direction vector is negative 2, 5, and 1. Now let's talk about the plane in R3. A line is given by a point and a direction. Similarly with the plane. A plane in R3 can be determined by a point, and the vector n is perpendicular to the entire plane. It is shown here. So I have a plane. If I give you a vector n, which is pointing upward, and I told you the plane is perpendicular to this vector, then you know that the plane will be like this. However, the plane could be at any level. So if I give you a specific point, then you can determine the plane. To find the equation of the plane, we can take any point on the plane, and let's call the point P. It has coordinates x, y, and z. We know that the plane is perpendicular to normal vector n. So the vector from P to P0 is perpendicular to n. So we get the first equation. Vector p0 to p dot with n equals to 0 because they are perpendicular. And we can rewrite the vector from p0 to p as vector p, which is vector from the origin to point p, minus vector from origin to p0. And this dot with n equals to 0. Then we can distribute the dot product and rewrite that as the third equation. P dot n minus p0 dot n equals to 0. Then we move the second term to the right hand side. We get p dot n equals to p0 dot n. P has components of x, y, and z, and n has components of a, b, and c. So p dot n, we get ax plus by plus cz. Similarly with the right hand side, p0 has components of x0, y0, and z0. But note that on the right hand side, a, b, and c are just the component of n, which are constant. x0, y0, and z0 are components of p0, which are also constant. So let's just call the right hand side as another number, d. So here is how we are going to denote equation of a plane. ax plus by plus cz equals to d, where a, b, and c are components of the normal vector n, and the d on the right hand side is the value after we plug in the coordinates of p0 to the left hand side. Let's look at this example. Let's find the equation for the plane through the point 2, 3, and 4, and the plane is perpendicular to the vector 1, negative 4, and 3. So from the question, we know that the vector given 1, negative 4, and 3 is the normal vector because the plane is perpendicular to this vector. And we also know that the plane passes through this point. Then the left hand side of the equation, we have ax plus by plus cz. Normal vector has components of 1, negative 4, and 3. So left hand side we have x plus 4y plus 3z. Then to find the constant d on the right hand side, we are going to plug in p0 into this equation. Then we get 2 minus 4 times y, which is 3, plus 3 times c, which is 4. That is 2 minus 12 plus 12, and that equals to 2. So here's the constant d. So the equation of the plane is x minus 4y plus 3z equals to 2. And that is the end of the video. In this video, we covered the lines and planes in R3. If you like my videos, please like and subscribe, and I'll see you in the next video.